Okay, so the last section for this exam 2 is sequences. We're going to change gears quite a bit here, and then the next exam will build on this quite a bit. So first of all, what is a sequence? Well, technically it's a function whose domain is the set of positive integers. So what does that mean? It's just a list of a first element, a second element, a third element, a fourth element, etc. Okay, it's just a list in an order. We are going to be dealing with infinite sequences, sequences that do not stop. They continue on, and of course the only question we can ask about these sequences is, well, are they heading to a number or not? That's it. And so really evaluating these sequences is going to be basically what? Taking a limit, right? What happens as these sequences go on and on? Does it approach a value or does it not? So here's the basic 3 ways to represent. This is all the same sequence. I don't usually use that. I use this one a lot, or I'll just list out the elements, right? So, this just means n goes from 1 to infinity. There, n is an integer. So it's 1, 2, 3, 4. Well, positive integers, actually. 1, 2, 3, 4. So when n is 1, you get a half, then you get 2/3, 3/4, etc. So these are the 3 ways to list out, basically the 3 ways to list out this particular type of sequence. And, like I said, I'll mainly use 2 and 3. You may see 1. You can also, you don't have to have a defining equation. So you can say, let an be the nth decimal representation of e, right? What's e? It's a number between 2 and 3. Well, there's number 2.71828, right? So this 7182818, this is a sequence which represents the nth decimal place of e. It does not have an equation. But it's still legit, and you can say, well, what happens to the sequence as n approaches infinity? So here again, what happens as n approaches infinity? Well, the only thing, like I said before, that you can do is take a limit, right? This is a very basic limit here. You should be able to do this very quickly, and in your head, hopefully, right? They both are increasing, so you just, right? What's the only technique for evaluating limits at infinity? You divide by the highest power of the bottom, and you would get 1. Which means the further out in this sequence you get, the closer to 1 you will get, right? The 10th term is close to 1. The 10,000th term is really close to 1. The 10 trillionth term is unbelievably close to 1. Okay? So the limit exists. I put this in here just, well, you're not going to be responsible for this, but remember we did, try not to cringe, right? So we said the limit as x approaches a of f of x is L. Like, what did that really mean, right? For all epsilon greater than 0, there exists, right, a delta greater than 0. Remember that? There is an analogous definition for infinity. This is it. We're not going to, I'll just tell you what it means. We're not going to deal with it. We're just going to deal with evaluating the limits. So the delta, there's no delta epsilon, because there's obviously n, it goes to infinity, so there's no delta. So the equivalent is for all epsilon greater than 0, there has to exist just as a natural number, 1, 2, 3, 4, 5, such that if you get past that natural number, then the difference between these two is less than any positive number. So it's an equivalent definition. It is the kind of the big boy or big girl definition of this limit as n goes to infinity. Again, we're not going to deal with it. You guys, I'm sure, had enough with this before, so but I'm just letting you know there is one. There it is. Again, same sort of thing that we talked about before, right? If the limit exists, then the sequence converges to that number, whatever number it is that you get. If the limit does not exist, sometimes limits don't exist, then we say the sequence diverges. And again, feel free to use capital C or capital D. Okay. Says we're going to review, you can review the limit laws. You should know these already. Squeeze theorem also applies. Again, we've covered that. You should know that already. Make sure you take a look at that if you're not sure. It's a little hazy. This is a good one to know. What does this say? If the limit of the absolute value of a sequence is 0, then the limit of the sequence itself is 0. Okay? You can actually use the squeeze theorem to prove this, but you just need to know the result. So if you take a look at the limit of the absolute value, in other words, make all the terms positive in a sequence, if that limit is 0, then the sequence itself also converges to 0. Right, same sort of deal here. You can still divide everything by n, and you get minus 1/2. So the sequence converges to that, right? The further out, the bigger n is, the closer this number will be to negative 1/2. How about this particular sequence here, right? Well, this one actually you can't do the highest power trick, right? That doesn't work. So what's going on here? Well, what happens to the top as n gets large? Well, it gets very large, right? And what happens to the bottom as n gets large? Well, it also gets very large. Well, gee, this looks familiar, right? Why can't we apply L'Hopital's? Well, you have to be very careful. L'Hopital's does not apply to sequences. Part of the L'Hopital definition, we didn't get into it, but it requires a function, and a continuous function at that. So you have to be very, very careful here. Now, let's take a look at the following. Excuse me. Let's actually use something even a little simpler. So let's say I want to do it over here. Let's take a look at this sequence of the function 1 over x versus the sequence 1 over n. Okay? So notice that if we were to graph the function, right, and we'll start at 1. So if we were to graph the function, it would kind of look like this, right? Agree? That would be the function 1 over x. Continuous function, goes to the right and continues on and on, etc. What if we were to, what is this equal to? What are the first few terms? Well, when n is 1, it's 1, comma. And when n is 2, it's a half, a third, a fourth, dot, 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 right? That's the sequence. Let's plot those points. 1, a half, a third, a fourth. Right. So what am I getting at here? Well, what's the difference between these two? Well, an, the sequence, is a bunch of points. F is the function. But notice that the points of the sequence are on the function. So what does that say about where the function goes versus where the sequence goes? Well, they both go to the same place because the sequence is on the function. Okay? So if one converges to a value, the other one does as well. Should seem reasonably okay to say that, right? So how do we get around this thing here if we want to use L'Hopital's? Well, we turn it into a function, okay? So we consider the function. Notice that all I did was exchange x for n. This we can use L'Hopital's on. You'll get 0. It converges to 0. Therefore, that implies the limit as n goes to infinity of n squared over 2 to the n minus 1 is also 0, okay? So you can apply L'Hopital's to the associated function. What does that mean for you guys in terms of an exam or something like that? Well, what it means is if I give you this, you're going to have to show me the x. Okay, and then you can see if you don't change the variable, I'm taking off points. Why? Not because I'm a jerk, but because the change in variable shows me you know that you can't apply L'Hopital's to a sequence and that you have to change it over to a function. And then you can apply it and then it goes to the same place. Okay, so that's the moral of the story. This basically sums up what we just said, right? If the limit of the function is L, then the associated sequence also converges to L. You don't have to prove that, you can just use that. But you do need to change the variable, please don't forget. Is this a convergent or divergent sequence? Well, it's certainly bounded, right? It's never greater than 4 or less than 2, right? It's 2, 4, 2, 4, 2, 4. So does this approach a single number? No. So it's divergent. So it can be bounded and still not converge. So the sequence r to the n is convergent if r is between minus 1 and 1. So you can just use this information going forward. You don't have to prove it or anything like that. The limit of r to the n as n approaches infinity. It's 0 if r is between minus 1 and 1. And if r is 1, it's 1. Obviously, if r is minus 1, what does it do there? Should be able to figure that out, right? Diverges, plus 1, minus 1, plus 1, minus 1. So last little bit and then a couple little definitions and then that's it for this section. So a sequence is monotone if the terms are non-decreasing or non-increasing. Okay, so what's with the silly language? Why not just say increasing or decreasing? Well, what does non-decreasing and non-increasing include that increasing and decreasing do not include? Well, the answer is staying the same. Okay, so non-decreasing means it's increasing or staying the same. So staying the same is still a monotone sequence. Okay, so 2, 2, 2, 2, 2, that's a monotone sequence. Even 2, 3, 3, 4, 5, 6, 6, 6, 7, 8, 8, like that's also a monotone. As long as the terms are not going, as long as the next term is greater than or equal to the previous or less than or equal to, it's actually a monotone sequence. We're going to come back to this in a second, but before we do, let's talk about this. So we say a sequence is bounded above if there exists, that's what that means, right? If there exists an m, which is a real number, such that an is less than or equal to m for all n, okay? If that's the case, then we say m is an upper bound, okay? So if we have the n over n plus 1, right, if we write out the first few terms of that, when n is 1, this is a sub n. When n is 1, we get 1/2. When n is 2, we get 2/3. When n is 3, we get 3/4, etc. So what is an upper bound of this sequence? Think about that for a second. What is, or even better, how many upper bounds are there for this sequence? That's an even better question. So some upper bounds. Maybe most of you will say probably 1 will be your first guess. That's correct. Is 2, is e, is pi, is 11, is the square root of 17, right? Yeah, all of those are upper bounds, right? Because the sequence is always less than or equal to all of those numbers. Okay, so this has an infinite number of upper bounds. But of all of these upper bounds, right, that was supposed to be highlighted, of all of these upper bounds, which one is the smallest? 1. Okay, it's called the least upper bound. We'll get to that in a second. So a sequence is bounded below, same exact idea, right? If there's a m such that an is greater than or equal to m for all n, okay, and it's called the lower bound. So this right here is a little bit beyond the scope of the course, which is okay. I'm just going to give it to you. It's kind of just interesting. So a sequence is bounded if it's bounded below or above. Doesn't matter. So one property of the real numbers, which is very nice, is they're what are called complete. So we don't need to know technically what that means, but informally, it just means there's no holes. So we can't say that about rationals, let's say, because between two rationals there are non-rational numbers, right? Irrationals. So the rationals are not complete. But between any two real numbers, there are only real numbers. So we say we can say it's complete. So this completeness property actually can show that if a sequence has an upper or lower bound, if it has an upper bound, then it has to have a least upper bound. And the fancy name for that is supremum. Okay? In other words, of all the upper bounds, one of them has to be the smallest. In this example, the supremum is 1. It's the least upper bound. LUB, least upper bound. And of course, there's also a greatest lower bound, and that's called an infimum. Okay, so real nice, dollar words there. Again, this is outside the scope of this course, but it's nice, I think, to mention some things like that and bring that kind of in. What do you need to know? You should know what an upper bound and a lower bound is in monotone. So why do I mention all this stuff? Well, just to finish it up with, we already talked about this, right? The least upper bound is 1. And we're going to finish it up with this. A monotone sequence theorem, right? Every bounded monotonic sequence has to be convergent. Every bounded monotonic sequence has to be convergent. So if it's bounded, think of this as a wall, right? And if the sequence is monotone, that means it's non-increasing or non-decreasing. So if this is our stick figure and they are walking this way, right? If they continue to walk this way, that's the monotone part, right? Because they can't go backwards. It's either forwards or stay the same. And the wall is the bounded part. What has to happen? Well, eventually the stick figure is going to hit the wall, right? So it has to be convergent. Monotone sequence theorem. So that will finish up the material for exam 2. Again, a couple of sequences. Do they converge or diverge? You're just taking limits here. Same with homework. And then you'll see that this is a nice launching pad into the next test material.